Hello and welcome back to Koi Does Leetcode. Today I'm going to be doing problem number 98, validate a binary search tree. So for this problem you're given the root of a binary tree and you need to determine if it is a valid binary search tree. So a binary search tree is a tree for which it's a binary tree for which if you look at the root node, everything in the left subtree for the root is less than the root, and everything in the right subtree is greater than the root. So you can see in this example 1, this is a binary search tree because the 1 is the only thing that's in the left of the root, and it's less than 2. And the 3 is greater than 2 and it's to the right. And also you have to be able to do that check for every single node. So the nodes that are to the left subtree of 1, it's no nodes, but if there were any nodes, they would have to be less than 1. And everything to the right, there are no nodes, but it would have to be greater than 1. It's either not there or it has to be greater than, or if it's to the right, or less than if it's to the left. And the same thing must be true for this 3. So you can see that example 1 is a binary search tree. But what about an example where it's not a binary search tree? So in example 2 that I've drawn for you here, we can see that 5 is the root and 1 is to the left of 5 and it is less than 5. So it is, it's doing what it's supposed to do. Now the 6 is greater than 5, but you have to consider every single thing in the right subtree needs to be greater than 5. And this 4 is not greater than 5. So this is not a binary search tree. So how can you determine whether or not it's a binary search tree? Well, it's pretty simple to do when you are looking at the tree. But how can you do this programmatically? Well, you can't just go at the root and look at the left child and the right child because you're not looking at the entire tree. So the entire tree needs to be less than the root. Less than the root if it's to the left and greater than the root if it's to the right. So you can't just look at the left child and the right child. And you can't like recursively look at the left child and the right child, because say you did that and you were at this 6 and you looked at the left child and the right child. Well, this 6, the left child is 4 and that's less than 6, and the right child is 7 and that's greater than 6. So it looks like it's a binary search tree, but actually you have to consider the whole subtree, the right subtree, and so this 4 is making this not a binary search tree. So what can we do? Well, we can use this special property of the in-order traversal of the binary search tree. So the in-order traversal of a binary search tree always gives you the sorted order of the nodes. So in-order traversal goes it goes left, root, right. So left, root, right. And that would be, for this first example, 1, 2, 3. So if you look at this whole thing is sorted, then you know that it is a binary search tree. But let's do the in-order traversal of this example 2 tree. Well, it would be go to all the way to the left, which is 1, and then go to the root, which is 5. Now go to the right subtree. Now you need to go all the way to the left, which is 4. Then you go to the root, which is 6. And then you go to the right, which is 7. So this is not sorted. You can see that this 4 comes after the 5. So you can see that the 4 is the thing that makes this not sorted, which is the same thing that is for the tree. This is what makes it not sorted. So you can tell that this is not a binary search tree, the in-order traversal. So that's what we can do for this algorithm is we can do the in-order traversal and then check if the in-order traversal is sorted. And how can you check if it's sorted? Well, if this is I and this is I plus 1, if I is less than I plus 1, the number at I and the number at I plus 1 is, if I is less than I plus 1, then it's sorted. But the number at I, so for these two, 1 and 5, 1 is less than 5, so that's sorted. But if you increase I to here and I plus 1 is here, well, 5 is not less than 4, so it's not sorted. And that's how you would do it. So let's code it up and see how it looks in code. So the first thing that you need to do is you need to do make a variable that's going to hold your traversal. So we're going to make a traversal variable. It's going to be a global variable, and we're going to make a function called inOrder that is going to do the inOrder traversal. So if not root, we're just going to be finished, so return. And so now you know that you have a root node. So inOrder goes left first, so we're going to go inOrder root.left, and then we process the node. So we're going to go traversal.append root.val, and then we're going to do our inOrder traversal on our right. So it goes left, root, right, inOrder root.right, and that's the end of our traversal algorithm. So at the end, we're just going to call inOrder traversal on the root node, and what that's going to do is that's going to update our traversal global variable. So in there we're going to have, so now our traversal has our inOrder traversal in order. So what we're going to do is we're going to also have another function. So we're going to have another function that is that's going to check is sorted, and we're going to give that our list. We're going to call it array, ARR for array, and we're going to loop over the list. So for I in range, and we're going to go from 0 to the length of the array minus 1, because we want to stop 2 before we get to the end of the list, because we're going to check I and I plus 1. So we want to check 2 before we get to the end of the list. So if the array at I, if not, the array at I is less than the array at I plus 1, if that's not true, then we're going to return false. And if we get through the entire list and it doesn't return false, then we want to return true. And that's how we can tell if it's sorted. So we run the in order traversal, and then that updates our traversal array, and then we return is sorted with our traversal as our array, and that is our answer. So this will run in O of n time. It'll be O of n time to do the in order traversal, and it'll be O of n time to check if it's sorted. So that's O of 2n, so that resolves to O of n time. And for the space complexity, the recursion would make this O of h for the height of the tree space. If it's a skewed tree, if it is not balanced, it would be if it's skewed all the way to the left or the right, it would be O of n space. And if it is balanced, then it would be O of log n space. So this is the code. So let's run it. And I forgot a colon here, and it is giving us the correct output. So let's submit, and it was accepted, and it's pretty fast. So that is how you determine if a binary tree is a valid binary search tree using an in order traversal. Thanks for watching, and I'll see you in the next video.